So the next talk is talk about short paper presentation, and the title is not short. The title is S4 modal sequent calculus as intermediate logic and intermediate language, and the talk is given by Jean.
Yes, Jean.
Jean, yeah, please.
Okay. Yeah. So hello, and I will talk about S4 modal logic and as a sequent calculus for it as an intermediate language. So in the programming language community, there has been a long-standing debate about the place of continuations. And in 2019, so there was this paper compiling with continuation or without whatever, in which the authors developed an intermediate language in which they have the second-class continuations, those are special continuations which cannot escape the scope, a C operator, like license, which implement double negation elimination, and a CPS translation that erases this operator. And they advocate for a syntax in which we can mix direct style and continuation passing style in the same language. And they showed that the notions of continuation they used in compiler intermediate language is different from the one we usually see in logic. So in logic, continuation are either used linearly or without any restrictions at all. So linearly used continuation corresponds to intuitionistic logic, and without restriction is classical logic. But in compilation, continuation is the second class, and in some sense intuitionistic, because adding those second class types and even a C operator restricted to these continuations does not increase the logical power of the first class fragment. So we studied the calculus to see exactly what is a second class continuations from a logical point of view. And so what exactly is a second class value? So these are values which cannot be returned from a function. They also cannot be referenced from a first class value. And in a language with mutability, they cannot be stored. And this ensures that second class values can be allocated on the stack. So for example, here this is the code a programmer would write. Big is a big expression. And it is then compared to this code. So we introduce a C operator, which introduces a continuation which is second class. We allocate a new continuation J, but it's a continuation, so it goes on the stack, and the big expression is only allocated once. We use it, and then when this code returns, the stack gets freed, and the big allocation is freed. Yes. Also, recently there have been lots of sequent calculus based intermediate representation for compilation, and those allow to manipulate continuation directly. So for example, there has been this paper about sequent core, so it's a compiler intermediate language for GHC based on sequent calculus. This paper used also compilable for sequent calculus based intermediate languages, and this one used specifically the fact that duplication and weakening rules are explicit in sequent calculus to implement reference counting. And so we showed that the calculus of with continuation or without whatever had in fact a sequent calculus. Because, for example, in the CPS translation, they separates functions returning something from functions which doesn't return, so jumps. And the rules of the CPS translation for lambda abstractions is different in the two cases and correspond exactly to the rule for introducing either arrows or negations in sequent calculus, based on if it returns something or not. And so in my master's thesis, I designed a sequent calculus So a sequent calculus-based language, so it's based on system L or mu-tilde calculus. And we can interpret the language into MIND, so system L-pole box, and we can interpret system L-pole box back into the language, but without the C operator. And this translation factorizes the CPS translations. So it's exactly in the middle point. My calculus is polarized, so it supports both call by value and call by name. And first class types are represented by using a modality box, which follows the laws of S4 logic, almost. So we have the usual rules of a common head, but the strongness is not totally valid because we have to introduce a polarity shift. So it's like adding unit implies B for the arrows is that. And this is because where modality and call by value is bit difficult together. And so why did we introduce this modality? Well, it's because to introduce a value, a first class value, we restrict the context so there's only first class type in the context. And to introduce values of modal types, to introduce a modal formula, we also restrict the context so there's nothing on the right and only formulas of modal formulas on the left. So exactly the same thing. And also, so in a polarized sequent calculus, polarity represents evaluation mode. So there's a positive polarity for call by value and negative polarity for call by name. And since we want modal types to be evaluated differently from non-modal type, we introduce a new polarity for them. And in this semantics, what we want is that modal values go on the heap and non-modal values on the stack. So we can combine types, and types have polarities too. And for example, a product of two types, the pairs, are modal if both components are modals or only call by value else. And so, yeah, we designed machine semantics with the same properties as the one of with continuation or without. So modal values, so first class goes on the heap, and everything else goes on the stack, especially continuations. And so in this semantics, when the evaluation of a modal term returns, the stack shrinks up to the stack how it was before the evaluation started. So this is implemented in this rule. So if we evaluate the value v against the continuation alpha, we retrieve the continuation associated to alpha, and we evaluate v in this new environment. But the stack shrinks up to alpha, and we drop everything allocated after alpha. Why is that sound? Because S has been allocated before, so it's good, and V is a modal value, so all its three variables are themselves modal, and so they have been allocated in the heap. And we retrieved exactly the stack discipline of with continuation or without, whatever, because when function returns, when returning first class types returns so modal types, well, it's an evaluation of a modal terms, so the stack shrinks. And if a modal argument is passed to a function, it is evaluated first, and so the stack can shrink after its evaluation again. However, we allow functions to return non-modal types. And in this case, things does not go that well. And values are still allocated in a stack-like manner, but this stack doesn't correspond to the evaluation stack anymore, to the call stack anymore. Because, for example, in this function, in this code, y is allocated on the stack if x is non-modal. But if the stack shrinks at the end of the evaluation, then it gets returned and dropped, so it doesn't work. And so, yes, the call stack is different from the stack in which we allocate. Okay, so in the title, I also spoke about intermediate logic. So the intuitionistic S4 logic has already been applied to compilations, but here we use really classical S4 logic. But at the same time, we expect intermediate languages to correspond to intermediate logic, that is, to be slightly weaker than full classical logic. And this is true if we restrict our calculus to the fragment in which functions return only modal types. But how are we stronger than intuitionistic logic? Thanks to the Gödel-McKinsey-Tarski theorem. Because this theorem says that intuitionistic logic is isomorphic to some fragment of S4 modal logic, and this fragment is included into the fragment in which functions return only modal types. So we really have, through the Curie-Howard correspondence, a logic which is between intuitionistic and classical logic, and which correspond to intermediate language. And so, yeah, what would I do later? Well, try to better understand the fragment of S4 in which we have efficient compilations, and maybe introduce a dual modality of S4, so the lozenge, because it plays nicer with negations, and try to apply that to efficient compilation of dependent types, and to designing dependent type series between intuitionistic and classical logic, because we know that if we have proof-relevant classical logic with dependent types, it's not sound, but maybe there's a design space between full classical logic and intuitionistic logic. Thanks for your attention.
Questions, please. Any question?
Actually,
Yeah. Just a moment. Yes.
This is a very basic question.
Yes.
Is this on? Oh yeah, it is. Okay. Very basic question about polarity in this. Does the polarity come from the, like, there's two senses of polarity that are out there. There's like the sense that I know of that is like Paul Levy sense from call by push value.
Yes.
Which seems more like what you're talking about.
Yes.
Okay. And then there's the other sense from like the invertibility of rules in sequent calculus. That might not be.
Actually, they are related.
They are related, yes.
Yes. But here we're not talking about, the different polarity of push values and the evaluation modes. So, yeah.
Okay, yeah, that was my question. Thank you.
Yeah.
Could you say a bit more about how you think this will help with efficient compilation of dependent type theories?
Yes, because if we extend this language to dependent types, we can handle better CPS translation of different types, and so it might be more efficient.
Mm-hmm. And do you see obstacles there? Or do you think that's going to be easy?
Actually, there have been some work called CPS translation for dependent types, which I don't remember well. But I think they have like special rules for type checking continuations. If we may remove these special ad hoc rules to have like only logical based rules for, at least for the modal fragment.
Great talk. Can you go back to the first page where you introduce the axioms of modal logic?
This one?
Yep. So there is a up double arrow.
Yes.
In axiom K.
Yeah.
I didn't see it like in the following definition of syntax. Could you say a bit more about it?
So yeah. You mean here?
Yep.
Yeah. Okay. So it's a negative shift. So it's like unit implies B.
Unit plus B. Why do you need it?
Well, so I don't know.
Why do you need it?
Okay, I need it because to introduce the rule for introducing a box only takes values, but this is a result of applying a functions. So if I will implement, I apply a function, and so I cannot just put it in the box. And if I say let x equal so application of this to that in box of x, then it's not well tied because x is a free variable which is not of modal type. It's of type B. So we have to delay the computations and put it into a function.
Okay, makes sense, thanks.
You say this is really S4 logic.
Yeah, so that's the question. In other work, for example, in the Ox-Camel paper, they also have the same kind of limitation. But in a paper of Curien, Marcelo, and Guillaume here, they actually have a same kind of modality, but they say that so they have an exponential modality which they decompose as something like this, then that. So maybe the real S1 modality would be box upshift of B, but they have to look at it further.
Thank you very much. Let's thank the speaker again. Yeah.